Hey everybody, Mr. D here checking in with concavity and the second derivative test. We're just coming fresh off learning about maximum and minimums, absolute and local, and also intervals of increase and decrease. So now what we're looking at is interpreting that one step further. Concavity, or at least concave up, means it's where the second derivative is greater than zero. Graphically, it basically looks like a bowl or a portion of a bowl. The other thing that you must note is that if you were to draw tangent lines, as is shown in those diagrams, that the tangent lines are always below the function when it's concave up. You'll see what I mean here. There's a tangent line. Oops. A tangent line here is below the function, below the function, below the function, below the function. Similarly in this shape here. The other thing you'll note when it's concave down, it'll be like a bowl that's upside down. If you think of a soup bowl, for example, or portion of a soup bowl. And in this case here, the tangent lines are above the function. So that's another tip. The bowl shape, or in this case here for concave down, the upside down bowl shape, or portion of an upside down bowl, but also the second derivative, the tangent lines lie above the function when it's concave down. And lastly, a point of inflection is the specific point where the function changes from a downward bowl to an upward bowl, or similarly an upward bowl to a downward bowl. So in other words, if we were to look at the colors we used before, a downward bowl would be concave down, and then we used yellow in the earlier example indicating concave up. So the point of inflection is right there, the point of inflection. Similarly, you can also have this scenario where you have a bowl opening upward, or at least a portion of the bowl opening upward, and then it transitions to a bowl opening downward. And then in this instance here, we have a point of inflection. So it's where there's a change in concavity. So that's a very important note. There must be a change in concavity as shown in that diagram. So let's look at an example, a graphical example that is. For each graph, identify the interval over which the graph is concave up and the interval or intervals over which the graph is concave down. So I was using a blue highlighter for concave down, so I'm going to continue to do that. So in part A, we have a function that is concave down, somewhere about there, and then it transitions to a concave up. And presumably they go on indefinitely, so I guess I could just kind of like show that here. Oops. So now, determine concave up. So, and concave down. So concave down is negative infinite all the way up to, let's say, -2. Concave up would be from -2 to positive infinite. Again, these are graphical, so they're kind of approximates. Once we do it algebraically, then we'll come up with like the absolute point of inflection without any sort of hedging or estimation, just like we've done somewhat in the graph. So going to part B, it looks like it starts with a conventional bowl shape, so that's concave up. I've been using yellow, so I mean there's no real rule for that. I'm just doing it for consistency purposes. So we have concave up, and it's going to stop somewhere in that neighborhood there. And then we also have another concave up here, a half bowl. And then in between there, we have half of a upside down bowl, which implies concave down. So let's go ahead and do that. So concave down is represented in blue. It goes from, what's this? Oh, it looks like it's -2 again, just by chance. So -2 and 0, that's the interval. Concave up goes from -infinite to -2. And 0 to positive infinite. So I hope that helps you understand graphical determination